Hello and welcome to my YouTube channel. In this video, we are going to discuss about analog to digital converters and how to program the analog to digital converter in Tiva C board. This is the first part of the video. In the second part, we will see the programming part. Now, first of all, let us discuss about ADC or analog to digital converter. Analog to digital converters are electronic devices, or we can say electronic peripherals inside the microcontrollers that converts analog signal to its equivalent digital value. Basically, all the signals that we get from the nature, for example, heat, sound, light, flow of air, temperature, all these quantities are analog quantities because they are always changing with respect to time. And therefore, to read these analog values in a digital system, we have to introduce analog to digital converters. So basically, analog to digital converters take analog voltage or current as input signal and they convert them to its equivalent digital values. The analog samples are read at a particular interval, and that is known as sampling period. And at each sampling point, the analog to digital converter reads the amplitude of the analog signal and converts it into its digital value. Basically, analog to digital converter performs two operations. First operation is called sampling and second operation is known as quantization. If we see in the XY axis, any analog signal, because here you can see the signal is varying randomly at every smallest time period. So if we divide these time periods and read the values of the analog signal, then this x-axis divided by small intervals is known as sampling. Whereas if we see the y-axis, if we divide the y-axis into smaller values, then we will call it quantization. So remember, sampling is always done in the x-axis, which is generally the time, and quantization is done in the y-axis, which is generally voltage or current. Now coming to sampling. So whenever we talk about any ADC, sampling is one of the most important parameters. It tells about the frequency at which the sampling will be done or how often the ADC will measure the analog signal and convert it into the equivalent digital value. Sampling therefore is performed in time axis and the units are generally samples per second or hertz, which is frequency, how frequently you are reading the samples. So to determine the minimum sampling period, we often refer to Nyquist criteria. Nyquist criteria says that in order to accurately reconstruct any analog signal from its digital samples, the sampling rate must be at least twice the highest frequency of the analog signal. Specifically, the sampling rate should be greater than or equal to twice the bandwidth of the analog signal. Mathematically, it is represented as sampling rate or the rate at which the sampling is done should be greater than or equal to 2 times the maximum frequency of the signal. Generally, this is the minimum value which should be met. Otherwise, in general, practically we use at least 10 times the frequency of the original signal. So this 2 is the minimum criteria provided by the Nyquist, but in general, today's practical scenario, we take the value at least 10. So here we can see the sampling in the signal done in the top figure is slower sampling rate. Therefore, we are reading the samples of the signal at a larger interval. Now, if you increase the sampling rate, you can see the signal is traced more closely in terms of sampling period. So, therefore, we should always go for higher sampling period to obtain the best possible fit of the analog signal. Now, coming to the quantization part, quantization is the process of converting the analog signal into its finite number of discrete levels in terms of voltage or current. So, ADC assigns a digital code to each sample of its amplitude, and these discrete levels are then resolved by the ADC. And generally, quantization is expressed in terms of bits. So, every A to D will be having one of the parameters, the bit. So, for example, if we have an 8-bit ADC, then that ADC can generate 2 to the power 8, that is 256 discrete levels. So, the signal can be divided into 256 different voltage levels. So, suppose if we increase the number of bits, suppose we have a 10-bit ADC, then the number of levels will be 2 to the power 10, that is 1024 discrete levels. So, suppose here we can see our analog signal, and we divide this analog signal into its discrete voltage levels, and each discrete voltage level is then provided a digital code. That code can be 3-bit, 4-bit, 8-bit, 10-bit, depending on the bit in the ADC. Now, coming to the applications of the ADC, ADCs are widely used in almost all the digital systems. For example, audio systems, video systems, even in instrumentation where we do data capturing and reconstruction, we use ADCs. In communication system, you take it 2D, 2G, 3G, 4G, any other communication system, you will find the sound, which is analog value, is converted to its equivalent digital value. Then it is also used in industrial control systems and also in many domain which is related to the signal processing. Now coming to the features of ADC available in the Tiva C board. First of all, the resolution, which is represented by the number of bits. So ADC in the Tiva C board is 12-bit ADC. Therefore, it can read up to 2 to the power 12, that is 4096 discrete voltage levels. So it is a very precise ADC. Now coming to the number of input channels in the Tiva C microcontroller. So Tiva C microcontroller has got 12 ADC. So therefore, you can connect 12 different sensors, be it sound sensor, temperature sensor, light sensor, any other sensor in these 12 channels. So the channels ranges from A0 to A11. Sampling rate is very high in case of Tiva C board. It can sample maximum at a rate of 1 million samples per second, which is a very fast sampling rate. Now coming to the input voltage range, the range of voltage which the ADCs of Tiva C board can handle is 0 to 3.3 volt. Of course, this 0 to 3.3 volt can be varied. That means this range can be varied if you follow the instructions in the data sheet. The ADC starts its conversion based on triggering, and Tiva C provides both software based triggering as well as hardware based triggering. So you can start the ADC process by using software triggered or hardware triggered events. Apart from that, ADC also supports direct memory access. Therefore, the DMA will allow automatically transferring the data between the ADC and memory so that we can reduce the workload of the CPU. So these are the basic features of Tiva C board's ADC. If you want to further read or understand more about the Tiva C's ADC, then please refer to the datasheet provided by the Texas Instruments. With this video, I would like to end the video. If you have not subscribed the channel, then I would like to request you to please subscribe the channel and please click the bell icon so that you can be notified whenever I upload a new video. If you have any doubts or suggestions, please share your doubts and suggestions in the comment section. Thank you and have a nice day.